All right, take a look around you. I mean, right now, chances are you can see concrete somewhere. In a building, a bridge, maybe just the sidewalk. It's literally the most common man-made material on Earth. But what if I told you it has this hidden strength, a secret superpower that we're really only just starting to figure out?
And that's not just me saying it. This is the exact question researchers at Aarhus University asked. It's such a cool thought, right? That this material we've been using for centuries might be fundamentally misunderstood, and that it's capable of so much more. This question, well, it's at the very heart of what we're going to explore today.
So, first up, the squeeze that strengthens. Yeah, to understand the superpower, we've got to look at what really makes concrete, well, concrete.
See, on its own, concrete's kind of a one-trick pony. It is amazing at handling compression, squeezing force. But if you try to stretch it or bend it too much, it gets brittle. It doesn't really give you a heads up, it just breaks. And yeah, that's why we put steel rebar inside it. But even that solution has its limits.
But here's where the big idea comes in. We know concrete loves being squeezed from the top and bottom. So, what happens if you also start squeezing it from all sides at once, kind of holding it all together?
And that brings us to this idea called confined concrete. The Aarhus University paper describes it perfectly. Think of it like an external compressive stress actively supporting a concrete column on the outside. Basically, you're giving the concrete a constant reinforcing hug.
And look, this isn't just some theory in a lab. We actually do this with really clever arrangements of steel reinforcement. As you can see right here, circular columns often use this continuous steel spiral, kind of like a spring, while the rectangular ones use a series of steel loops we call ties. Both setups create that all-important sideways pressure.
So what does this squeeze actually do for the concrete?
Well, it dramatically improves two super important things, its strength and its ductility. Okay, let's just make sure we're on the same page. Strength is pretty easy to understand. It's the max amount of force something can take. But ductility? Ductility is really the unsung hero of safety in structures. It's a material's ability to bend, to stretch, to deform and kind of groan under pressure instead of just snapping in an instant.
And wow, this graph shows the difference perfectly. This is a classic stress-strain curve. So the up and down axis is stress. Think of it as strength. The side-to-side axis is strain, or how much it deforms. Now look at the curve for confined concrete. Not only does it reach a higher peak, which means more strength, but check out that long, flat tail. That is ductility in action.
And the real takeaway here isn't just about numbers on a chart. That extra ductility, it's the difference between a building just collapsing without warning during an earthquake and one that visibly cracks and sags, giving people inside that crucial time they need to get out. It's a huge, huge leap forward for safety.
All right, so how do we even know all this is true? Well, next, we're going to look at how we model this power, because the science here is solid and it's backed up by some really precise math. This isn't just guesswork. The effects of confinement are so well understood now that engineers have developed these complex models to predict exactly how a confined concrete column is going to behave under pressure. Don't worry, we won't get lost in the equations, but we can look at the results. And check this out. This shows you just how accurate these models are. The dark diamonds, that's real-world experimental data from a test in a lab, and the pink line, that's what the mathematical model predicted would happen. Just look at how closely they line up. It's an absolutely incredible validation of the whole idea. And hey, it's not a fluke. Here's another test showing the exact same thing. The model's prediction just about perfectly tracks the real-world results. This isn't random, it's a reliable, predictable phenomenon.
So we've got a stronger, more predictable, and safer material. What does this actually mean for you and me, for the world we live in?
This is the real payoff. By properly factoring in the effects of confinement, which, believe it or not, are often overlooked in standard design, we could build structures that are way stronger, allowing for these incredible, grander designs. They could be thinner, so we use less concrete, which saves money and is way better for the environment. And, like we've seen, they can be so much safer.
At the end of the day, unlocking this hidden superpower lets us build a better world. We're talking more efficient, more sustainable, and more resilient infrastructure that can stand up to the forces of nature and the test of time. It really makes you wonder, doesn't it? Concrete seemed so simple, so basic. We thought we knew everything about it. But just by looking a little closer, by asking the right questions, we found this incredible hidden potential. So it just leaves you with one last thought. What other unseen forces, what other hidden superpowers are just waiting to be discovered in the everyday materials that build our world?